In the movie Wizard of Oz, there's a scene where Dorothy and her friends finally get to meet the wizard. This is after going through all kinds of trials and tribulations. Of course, Dorothy was just trying to get home. And they ended up in the Emerald City, and they finally got an appointment to see the wizard. And they went in there, and there's this big screen thing, you know, there's fire and smoke going on. And in the process of you know, being scared by this entity that they were confronting, this wizard they've gone all this way to see, Toto goes over and pulls over the drapes, and you see a guy back there operating kind of a control panel, and the guy says, of course this is the actual wizard, he says, "Ignore the man behind the curtain." Obviously the implications were that it was just a big ruse. The wizard, there really was nothing, you know, behind him. He was just putting it on. Well, I think I know who that was really about. It was a gentleman named Walter James Espy. Walter James Espy. And he's called the Storm King. He is considered the father of meteorology. He lived back in the 1840s, and he's the one who developed this notion of convection, which to this day survives as the prevailing notion of how water gets up high in the atmosphere. But let me tell you how I came to find out about Walter James Espy. You see, back in the early 1990s, I took a class in meteorology. It was an elective. It was something I wanted to take. And I went in there because I had a particular issue. I had a question in mind. Let's put it this way. Everybody knows the temperature that steam or that water boils at to produce steam. And everyone knows that that temperature is much higher than anything in our ambient environment. Now here's the issue I had. I had done some research before I even went into this class about the concept of convection. And according to what I was seeing there, it indicated that convection involves steam existing in our ambient environment. Now, it gets really confusing if you think about it. Right now, there's moisture in the air all around me. And there's moisture literally in the air between me and the camera right here. But we don't see it. So you might come to the conclusion, well, that's because it's steam or it's in a monomolecular state. But that contradicts this notion. That contradicts this notion that steam can exist at such low temperatures. And that's the issue I had. And I went into the class with hoping to get some kind of resolution on this. And I guess I caused a little bit of a disruption. I'll tell you what that amounted to. You see, the teacher literally asked me to stop attending class. She did it in a nice way, though. She said, "Jim, I have a special project I'd like you to look into, and your unique vision on this particular issue is something I want you to examine during class time." And she even kind of hinted to me that, you know, she's going to give me an A in the class because I was doing all right in the class. And she said she wanted me to look into this gentleman, Walter James Espy. And she wanted me to come to resolution on the exact issue that I had been bringing up in class. I found out later that her real motivation was to get me out of class because I was just being disruptive, I guess, in retrospect. So I spent a considerable amount of time looking into Walter James Espy, but it wasn't just, you know, a random thing. I wasn't just, you know, doing a biographical examination, even though he turned out to be a pretty interesting guy. She wanted me to look into his science. She wanted me to come to grips with what he was telling us. And I was happy to do that because, frankly, that's what I had gone into the class for originally. So in the context of doing this research, I eventually got to where I felt like I understood the subject and I had something important to say about it. And I asked the teacher, I said, "Hey, would you like me to tell the class of my results?" And she said, "Well, you know, tell me what you got here." I go, "Well, it's pretty straightforward. This guy, Walter James Espy, is a quack. He's basically telling us things that aren't true. I looked into his research. he apparently did all these experiments, and the experiments were inconclusive. They didn't substantiate the notion that moist air actually turns to steam in our ambient environment. And so he really didn't substantiate the notion that convection is even possible. And therefore, I would, I'd like to be able to tell the class about it. She says, well, wait a minute, Jim. You say, convection isn't possible. Tell us now. We all know, common observation shows us that there's moisture way up high in the atmosphere. This has been noted in many different ways. Aircraft note this. It's a problem for aircraft. And it goes pretty far up there, up to the top of the troposphere. So Jim, you're telling us this guy, Walter James Espy, is a quack. But can you tell us how moisture gets up so far in the atmosphere? And also, can you tell us why it is such a big part of storms? So I accepted the challenge. And I undertook it with a lot of resolve and a lot of confidence that I would bring answers to these issues. And so I went into the library and I started looking up literature on water and getting an understanding of what it does under different conditions. And ended up just totally confused. I just simply couldn't make any headway. I couldn't make any sense. I, kind of went back to my teacher with my tail behind between my legs and explained to her that, water was a difficult situation. It was a real challenge, and it just left me confused. And I was very humbled by that experience. But I learned some things. She also asked me some other rhetorical questions that kind of made sense to me when I thought about it a little bit. One of those was, think about it. Do we want to go around telling people that major concepts in meteorology are nonsense? Whether or not the science is perfect, it's best if people take the word of meteorologists and at least trust that they know what they're talking about, even if their understanding isn't perfect, because it's kind of a public safety thing. You can't have people ignoring warnings and that kind of stuff. So I kind of understand it from that perspective. But more importantly, I learned that a lot of the major concepts in meteorology, things that are taken for granted, really don't make sense. Among those being convection, or at least, moist air convection. And if you think about it, there's common observations you can do that will show you that convection really doesn't have much to do with our atmosphere. One of those being, look at a cloud. Now, a cloud indisputably has larger drops of water in it. And if the weight of the cloud really made a lot of difference to what was going on, you would see clouds dropping out of the sky like rocks. And we don't see that. So there's something else keeping water suspended in our atmosphere. This was really clear to me. It didn't have anything to do with convection. Another notion, though, that was kind of related to that was how the water gets up into the air in the first place. Part of my examination involved the realization that evaporation also could not be a process that produces steam or a process that produces monomolecular H2O. And so the fact that evaporation takes place and actually pulls air up into it actually involves droplets of water that are heavier than the surrounding air. So there's definitely a force going on in our ambient environment that's pulling water up into the atmosphere. And it's doesn't have anything to do with water turning to steam. Evaporation is a process, or was a process at that time. Now I think I figured it out, but is a process, or was a process, that is somewhat mysterious. And as I continued looking into meteorology, I started to realize there's a lot of other concepts that also just simply don't quite add up. Another one is, in a thunderstorm, it's commonly known by aircraft pilots that the tops of thunderstorms are especially violent. There's a lot of activity going on up there. It's a very dangerous thing. Planes can get knocked out of the air very easily by the amount of energy that's taking place up there. And if you think about it, that in itself is a refutation of the concept of convection, because if air is moving up, you would think the top of the clouds would be just a very quiet environment, because this is where the upward motion came to a rest. But apparently exactly the opposite is the case. It's a very violent thing up there. Another concept that I came to understand was mistaken is the concept of jet streams. If you think about it, we don't really have an explanation for jet streams. We know there's these streams in the air and they move at relatively high speeds, and they somehow keep a relatively tight focus, kind of an isolation from the rest of the atmosphere up there. And they're pretty high too. They're up at the top of the troposphere. So there's another piece of the puzzle that wasn't making quite sense. And there's another one called CAT. CAT is just an acronym for Clear Air Turbulence. And it's the fact that very often turbulence happens right in the middle of perfectly clear air. You can think of it as being as if there's a clear stream in the air and a plane crosses into that path, and that too can be kind of dangerous to aircraft, and they're completely unpredictable because you can't see them. Now, many years have passed since that experience, but over that time I kind of approached things a little bit differently than most people would, because I knew that what was going on in the atmosphere wasn't well explained. And I kind of kept my ears open. I would watch a lot of TV shows, anything I could find that would maybe in some way help explain some of these things. Among those were shows like NOVA's Deadliest Tornadoes, and also shows that it involved an explanation of the solar wind coming from outside of Earth's atmosphere and entering through the upper atmosphere. And maybe I can just talk about that last one here a little bit, because it kind of answered one of the bigger questions, and that was the nature of evaporation. I kind of came to the conclusion that the reason there's evaporation going on in our environment is because all this energy comes in from above. It goes into our atmosphere. We think of it as static electricity. And this electricity, if I understand correctly, is mostly negatively charged. And water droplets have an outer boundary that is positively charged, and you take those two together and it creates evaporation. And evaporation, I'm pretty sure, you can debate this if you want, but evaporation, if I understand correctly, has something to do with electric charges that literally pull water up into the ambient air. And that, for example, is why on very dry days you can get dry, windy days, you can get static electricity charges, whereas on moisture days you can't do it because the charges are more balanced out. Now, it's important to understand, though, this explains how moisture gets up into our atmosphere, maybe 1,000 feet, something like that. And one of the phenomena that's associated with is something called an invection layer, invection layer. And one of the interesting things about this, though, is that this heavier air, and that's important to understand now, this moist air is heavier air, can, under very calm conditions, pool up and form relatively smooth boundary layers. And there's even pictures of this where where the moisture gets into such large droplets that you can see it, and it almost kind of looks like, looking from very long distances or far away, it looks like a lake, You get these flat boundaries, and they form in the lower atmosphere. Now, this still didn't solve the bigger conundrum, and that being how it gets from this lower atmosphere up into the upper atmosphere. And this is where that other TV show I mentioned kind of came into the picture, and that's NOVA's documentaries they do on tornadoes. And they're giving us some really great visuals on a tornado. And what's great about it is you can really see the structure that exists in the cone or vortex of a tornado. Now, to me, this explains, and this is associated with storms, and of course storms are wet. So you put those pieces together, and you consider that these tubes are basically pulling air straight up, creating updrafts. this kind of started to complete the puzzle. This kind of started to explain how air gets from the lower atmosphere up into the upper atmosphere, and also explains why storms are wet. But there's a really important point that I grasped from that apparently is controversial because other people don't seem to latch onto this notion very well. And that is, when I was looking at that tornado, and I was looking at that structure, I was asking myself a question, well, what can cause that? What is underlying the molecular basis of that? And I came up with the notion of a plasma. But before I get into the details of the particular type of plasma that I suggest, I want to give you some indication of why that was such an attractive notion to me. And it's because plasmas share two qualities with solids that, for example, liquids or gases don't have. And one of those qualities is that a plasma actually has a surface. Now that's important because if you're going to be trying to describe how jet streams form, for example, or tornadoes form, for example, part of your explanation is going to have to understand how energy tends to get concentrated in a stream flow. And the thing about a surface is it has the ability to reflect energy into a stream flow. That's a big deal if you're trying to understand the nature of, stream flow in the atmosphere. Another quality of a plasma is that it has the ability to assume and maintain some type of a structure. Again, that's a quality it shares with solids and something that gases and liquids don't have. Now, to start to put the pictures of this puzzle together now, we have this plasma, and this plasma has the ability to reflect energy into a stream flow. That means that the stream can actually start over long distances now. Keep in mind, flat surfaces over long distances, it can start to accelerate or actually start to gain momentum. And as it gains momentum, you start having the possibility of aerodynamic effects, specifically the Bernoulli Effect. And then the Bernoulli Effect will tend to literally reduce the pressure where that stream flow is and start to pull it up. Now, you take that Bernoulli Effect and you combine it with another effect called the Coriolis Effect, and then you can imagine how these sheets of relatively flat plasma can start to get pulled up and twisted, and they might even start to spin. And then you have the formation of some kind of a tube, and a tube is even a better environment for making stream flows happen, because a tube actually isolates the contents of the tube from the friction of the atmosphere. Now you can think of tubes happening over, think about it, hundreds of miles, a tube. It doesn't going to take much difference in pressure over that hundreds of miles for that air in there to start to accelerate, to go a little bit faster over amount of time. In fact, I even saw something on the internet where somebody came up with an idea that's pretty crazy, by the way, of setting up a tube that over, let's say, 1,000 miles or something like that, and using that and getting the energy out of it based on the fact that the pressure at one end is different than the other one, and tapping into that energy. Of course, a plasma is not exactly a very accessible thing to attempt to introduce to people or explain to people. We can look at plasma from the perspective of how a physicist would look at it. And normally a plasma is associated with ions that are being bombarded with a lot of energy externally. And that energy pulls ions apart, one being negatively charged, the other being positively charged, and they're trying to get back together. And as they're trying to get back together, the energy that's constantly flowing in keeps pulling them apart. And they form this kind of a active situation, and that's normally what we think of as a plasma. But now I'm saying that there's actually a plasma in the atmosphere, and it's operational, and it's involved in storms. But let's face it, so far I haven't really given you any kind of a firm understanding of how there's a plasma involved here. And that's because my idea for the plasma kind of comes from my understanding of water. And I think I mentioned I was watching some other TV shows. Well, here's a TV show that really got me starting to thinking along the lines of how water can actually has properties to allow it to behave like a plasma under certain conditions. The TV show I saw was from the History Channel, and it was Modern Marvels, and it was all about water. And it went into considerable detail about, and as you know, I had a history with water. Water was a real problem for me back in college. It was a real embarrassment, to tell you the truth. And so it was kind of a little bit refreshing to see this TV show, and they were talking about, hey, there's some things going on with water that simply aren't well explained. And there's especially something going on with hydrogen bonding. And so I kind of latched on to that notion. Might hydrogen bonding explain how water acts as a plasma in the atmosphere? And this will explain the tubes that I associate with the jet streams and the tubes that can be seen as part of tornadoes. And this also might explain the nature of evaporation. As you mentioned, we said it had something to do with electricity being pulled up into the lower atmosphere. So if it's true that water can somehow form a plasma in the atmosphere, I figured that if I went in and just did some more examination of water, that I could find out what was going on in that regards. And I did come across an understanding that I think, does a pretty good job of addressing that issue. And that's this notion that water has surface tension. This is something you might want to look up. It's really an interesting topic because apparently along the surface of water, there's a higher strength form of water, or less fluid form of water along the surface. And what I found interesting about that notion was I asked myself, well, if the surface tension of water increases its strength, then if you were to maximize the surface area of water, wouldn't that produce a higher strength form of water? And might, considering the fact that hydrogen bonds might be involved, and that hydrogen bonds, as I was coming to understand, were actually electromagnetic energy, or electromagnetically charged thing, might this expansion of, or this increase in surface area that produces a higher degree of surface tension, might that also produce some kind of a electromagnetic charge, or a situation where it produced a plasma effect? In other words, the energy was coming in that was pulling them apart, but because of this increased surface tension, they were trying to pull back together, and when you put those two together, you had a plasma effect. Well, that's when I kind of put two and two together. I thought about, what really was going on in these theoretical sheets of moist air with drier air above it and with wind going across it. And the concept that, and this is a standard concept in meteorology, it's called wind shear. The idea is that that you have two bodies of air that have two different levels of moisture. One being moist air, obviously, and the other one being dry air, and they're going in different directions, or not exactly the same direction. And along that surface, there's bombardment of the water molecules going on from the dry layer, right along that surface. And I thought to myself, well, what might that involve? What might it look like if you were to actually see it on a microscopic scale? And I imagine these little droplets being bombarded with side-glancing blows from air, and they would start to spin. And as they would start to spin, they would start to elongate, and they would tend to be pulled apart. And as they tend to be pulled apart, their surface tensional forces would start to be activated, and that would allow them to actually kind of form into like a little polymer in a sense. And with centrifugal force spinning faster and faster and faster, this could form, this was, I thought, close enough. This would explain how the surface area of the water was being maximized. That would explain how the surface tension was being maximized. And the net effect of this energy coming in from wind shear would explain how it all together effectuated a plasma. So I decided, instead of trying to convince people of this just based on what I just told you right now, I would get into water. I would get into examining what's going on with the hydrogen bonding of water. And that was not something I really looked forward to, because as I mentioned before, I had had previous experience, and that experience wasn't very good. Water was a difficult subject. And that turned out to still be the case. Now, I've written a paper on the hydrogen bonding. The name of the paper is Hydrogen Bonding Neutralizes H2O Polarity. You can find it on the internet. You can find it simply by Googling that phrase I just stated, and my first and last name, which is James McGinn. I'll spell the last name. It's McGinn. Now, I also have a book on tornadoes, and you can find that on Amazon. Again, I think you could find that just simply by doing a search on my name. So far, I've had a handful of conversations with the professionals in the field of physical chemistry who study water, and I tend to see a lot of the same things over and over again. I want to tell you about what I'm noticing. Basically, it's three things. First thing I'm noticing is they don't really have an appreciation for getting an in-depth understanding of hydrogen bonding. They seem to take it for granted a little bit, and they treat it, well, as I indicated, it's not a constant. It's a variable, and I explained why I think it's a variable. I've tried to get that point across to them. They seem to not think that's even something to be concerned about, which seems strange to me because, in my mind, it is the polarity of H2O molecule and its hydrogen bonding is the distinguishing characteristic that separates H2O from just about everything else. Another thing I noticed is there is this problem of amount of space that's existing between the molecules within a volume of water. You can do calculations on the size of an H2O molecule, and you can do on the weight, and you can understand that within H2O there is a certain amount of space in there. And this space needs some kind of explanation, and right now there's kind of debates about it. But it turns out there's like about every single one of these people, I'd say there are about 5 or 6 of them I've talked to, no one's had the same explanation. Now, they're not hiding this so much, but they are kind of minimizing it. What I mean by that is they're kind of playing it down as if, hey, we got everything figured out, except we don't have this one little thing, this space in here. We don't quite understand what this is. Now, another one that I think I just mentioned, so I'm not going to go into it too deeply here, but it's just this notion of this idealized notion that ice is water that arranges itself in a lattice. I think that's a bad notion. But another big thing that I notice is the term anomalies. Water has anomalies has kind of become a crutch for them. It's like they have this theory, and this theory covers, they think they got it all figured out, and anything that doesn't fit into the theory, well, that's an anomaly. Well, I think we got to go beyond just listing anomalies and calling that science. If we're going to do science, we have to have the guts to throw out our theories if the theories aren't working. And that's what's happening. The theory just simply isn't working. When it is difficult, it's most likely because they don't know, and they don't really want to be perfectly honest about the fact that they don't know. It's not unusual. It's part of human reality, not being honest. Don't take it personally, but don't take it either. So anyways, I've had a great time doing these videos, and looking forward to if anyone has any feedback, maybe give you some specific feedback on what questions you'd like to have answered. I'd love to do that. Tell me, hey, what question, or even try to come up with an observation that disputes what I'm saying. Hurricanes, for example. Jim, can you explain hurricanes? Yeah, hurricanes are explained by convection. So there's got to be some understanding of why hurricanes happen. Also, that hurricanes happen not when the jet stream is local, but when the jet stream is pretty far away. That's kind of an interesting issue in and of itself. But I look forward to anyone having any challenges, anything I have to say, and thank you. And remember, just because someone tells you something's true in science, don't just take their word on it. If something is true in science and you find a discrepancy, you ask them if they can explain that discrepancy. You'll find very often that they can't explain that discrepancy. Instead, they'll send you on some degree of a wild goose chase. and they'll tell you the answer is out there somewhere, and they'll kind of imply that I'm just too important to actually answer your question. Hey, no one in science is too important to answer questions, and no question is really that hard that you can't give them a specific answer, or at least point somebody in the right direction so they can find the answer. So, you know, don't bother people. They have to, you know, don't get on people's case if they don't give you the right answer. But don't just take it for granted. Do your own research. Go out and find out what's going on.